introduction. As I say, this is the Doctoral Training Centre's outreach show here called the Oddities of Science. And the show's actually being performed by a new cohort of PhD students from the Controlled Quantum Dynamics group. Now, before we get started, before they get started, I'd like to talk about one of my favourite oddities of science. And probably not this suit, but it's the microwave oven. Now, I know you're probably thinking you come here and you've got to get a talk on the microwave oven. Not exactly the most exciting thing. But you may have noticed that if you ever put food inside a microwave oven, sometimes it stays hot in places, sometimes it stays cold in places. Well, why is that actually happening? Well, actually, I'm not going to tell you, I'm going to show you. But it's not to do with convection or conduction, it's to do with another effect that hopefully Joe and the following students are going to tell you about. And it's best shown if I use one of these. Now, most of you, which is quite worrying about all the schools here, weren't probably even born in the late 80s or early 90s, but this is one of these t-shirts called Global Hypercolour. And people used to wear them in the 80s and 90s, and as you got hotter, they changed colour. So you can imagine why it never caught on, because there was only certain areas in which they did change colour. But this one here, when it gets hot, when it's cold and purple, I should say, and when it gets hot, is pink. So if I place it inside our microwave oven here, which I should say has a thing, which is a bit disappointing, turn it on, and I'll switch over to our camera. Hopefully it won't catch fire. That happened once, but don't worry. Right, there's some banging. I think we're done. Hopefully you can see that in certain areas. Right. Hopefully you'll be able to see in certain areas it's gone hot, in certain areas it's gone cold. Now, as I say, I'm not going to tell you why. We're going to find out in a minute. But the thing is, if I was to shrink you down to the size of an ant, or actually I was going to place ants inside, but I was a bit worried people with their sensibility would get upset. But if you were to place ants inside this microwave, or yourselves, shrunk down, you could actually navigate your way around these cold regions, actually, and you'd be perfectly safe. Now, I don't suggest any of you try and do that with ants, but you can do it. And they will be okay, because hopefully their little antennas will find the warm and cold spots. But going forwards, I'd like to introduce you, and hopefully explain why this is happening, our first speaker, and this is Joe, and he's going to be talking about resonance. So please give a warm round of applause to Joe.
So today I'm going to show you something you never expect to see with sound. So here I've got a thin piece of metal, and it's attached to a machine that can vibrate up and down at a frequency that I can choose. Now I've just got some ordinary table saw. Fill that all over it. Now watch what happens when I turn this on.
America who, during the Gulf War, actually tried to use sound as a weapon. And what they did was try to have interference. It would actually only focus sounds down to a very narrow beam. And they were trying to target soldiers, that they could target sound onto them and then make them hear sounds, and then the person next to them couldn't actually hear anything, hoping that they would think that they're either hearing voices in their head or actually hearing God, who would then tell them to no longer start fighting. So it has been used. There's other reasons as well. Some of you may have heard about the brown note that can actually cause problems with your stomach. That is actually an urban myth. But it has been tried, not by me, but some people have tried to do that. But anyway, on that note, which probably isn't the best one, but I'd like to introduce our next speaker. This is Naomi, who also is going to be talking about resonance and harmonics.
And that property is resonance. So this is a property of the object itself. So I've got some pictures up here, and they all look quite different, but actually all of these things have this property of resonance. So we've got the swing, the radio, the guitar, and this glass shattering. So all of these objects have a particular frequency at which they like to vibrate, so a particular frequency at which they get excited. So if we take the example of the swing, we all know that when you go to the playground, if you're pushing the swing and you push it really quickly, nothing really happens. It just sort of wobbles around a little bit at the bottom. Also, if you push it very slowly, similar, it just sort of follows your hands and doesn't get excited. On the other hand, if you push it at just the right frequency and give it a push every time it comes back to you, the amplitude is going to grow and grow. It's going to get excited, and that's resonance. And the same principle applies in all of these different cases in slightly different ways. So in the radio, it's an electrical circuit which is being excited, which is allowing you to pick up a signal. In the case of the guitar, just like Joe's been talking about, the whole body of the instrument resonates and allows you to hear a sound. And in the case of the glass, if you play a note at just the right frequency, the whole thing gets excited, starts vibrating so much that it can simply break itself apart. And this is just 4 examples, but actually resonance is just about everywhere. And there's a huge number of other examples I could show you to put up here, where we find resonance in everyday life. So, for example, in MRI scans, this uses resonance of molecules inside your body to be able to take internal pictures. Or in your iPhone, you're using resonance all the time every time you make a phone call. And even in the human body, so the ear uses resonance for you to be able to hear a sound. And I want to demonstrate to you another place where we can see resonance, which is in this piece of jelly, which I have in fact some light. So you can see. I think it's better with the lights on.
There you go. Right.
So I've got some jelly on this plate, and I'm going to turn on the power. So at the moment this is off resonance, the jelly's just sort of shaking a little bit. And now I'm going to tune it up to its resonance. You can see the pieces start to distort. I'm working even more. Some of them might start hopping off. This one's moving around. And they go crazy. Some of them even broke earlier when I was doing it. And then as they move off resonance, oscillations die away and it stops shaking. So that's just another example of somewhere where you can find it. And we can have this one. So the jelly is just an example of somewhere where we find resonance just in everyday life. But it's also something we found in the most complex scientific experiments where the LHC at CERN uses the resonance of fundamental particles in order to be able to detect them. And also something we find on very larger scales, even in natural solar systems or galaxies, to very smaller scales in atoms. And it's principles like these that we found across such a broad range of scales in different locations that make these physical concepts so interesting and fascinating to study. So I think I've run out of time to give you even more examples, but do come and find me at the end and have a look at my jelly wrestling.
Teachers in here tonight. When I was at school, my physics teacher actually worked for NATO before he became a teacher. And during the 50s and 60s, they found out a problem with helicopters, or certain types of helicopters, I won't tell you which ones, but they kept crashing, and they didn't know why. Now, after a while, they interviewed some of the surviving pilots, and they tried to figure out what was going on. And what they found was, just before the helicopters crashed, the pilot's vision was going blurry or they'd black out completely. And what they found out was that the rotor blades rotating, the humming from it, was actually the same resonance frequency as the liquid inside the eyeball, which is pretty similar to the jelly. So at certain speeds, the eyeballs were completely changing shape, and the pilots could no longer see where they're going, or the pain would actually cause them to black out. Now, he did assure me, these helicopters are actually still in use, he did assure me that they, and you might actually, depending on your career, flying them, he did assure me that they'd solved the problem, but, and there, well, isn't so many crashes now anyway, but hopefully, if any of you do fly a helicopter, that's something to bear in mind. Now, again, I'm not doing very well with these